Alright, thanks for watching, and today I want to show you something unbelievable. I actually want to show you that the family of function, sine of nx actually goes to 0. Which is very paradoxical, but it's rigorous and it's true. In other words, mathematically, I want to show you that if you take those sine waves and make them wiggle more and more, think like sine of 2x, sine of 3x, etc., etc., somehow, in the limit, you get the 0 function. And I don't know if you've seen this, but with those EKGs, you see someone like heart pumping faster and faster, and after a while it sort of goes to 0. Well, mathematically, I want to show you that. However, there is a trick, not trick, but like something to be careful about. The way I show it is 0 is really by defining what this converges to means. And because someone asked, I thought maybe I should also do a review of different types of convergence. So what does this arrow mean? For different people, it means different things. First of all, it could mean pointwise convergence. So first, let me talk about pointwise convergence. And this is sort of the most intuitive type of convergence. This would mean that simply sine of nx goes to 0 for every x. In other words, if you fix x and you consider those functions here, then eventually those functions go to 0. So that would mean something like that. Namely, if you take x, eventually the height of those things go to 0, which unfortunately it's not true. Because, for example, take x equal to pi over 2, then this would mean sine of pi n, should have written pi m, over 2 goes to 0. But that's not quite true, because sine of pi n over 2, it wiggles between 0, 1, minus 0, 1, minus, sorry, 1, 0, minus 1, 0, 1, 0, minus 1, 0. So it's not quite true because, again, those functions also intuitively, they go up and down. So unfortunately, pointwise, this doesn't make sense. So pointwise, it doesn't go to 0. There's something else called uniform convergence. Convergence. I don't really like that word uniform because it doesn't explain really what it is, but I prefer the term sort of independent convergence because sine of nx converges uniformly, so maybe double arrow, to 0. It means, it's a bit hard to explain. It first of all means that it's pointwise, goes to 0. And moreover, if you do an epsilon delta argument, so for all x, as n goes to infinity, if you do an epsilon delta argument, or I guess in this case an epsilon n naught argument, basically this parameter n naught doesn't depend on x at all. So n naught, I guess, or delta, doesn't depend on x. It's sort of independent of x. On x. And let me illustrate first of all, it clearly doesn't converge uniformly to 0 because it doesn't converge pointwise to 0. So this is a bit of a stupid example. But here's another example that's maybe more interesting. So consider the interval 0, 1 and the functions x to the n. So I guess it's x squared, x cubed, x to the fourth, and then x to the n. Right. Well, first of all, if it converges pointwise, it converges pointwise to the function that's 0 here, and at 1 it's 1. Because if x is between 0 and 1, x to the n goes to 0, but at 1, all those functions are just 1, so they converge to 1. And what I'm claiming here is the convergence is pointwise, but it's not uniform. And the reason is basically, let's say at 0, it converges to 0, but then somehow at 1, the convergence is slightly different. You can't really treat the convergence the same as 1 than at 0, and mathematically it means this n naught, right, kind of depends on the position you're in. So in other words, the convergence, again, depends on the position x that you're in, and it's not uniform convergence. Uniform convergence would really mean it goes to 0 in the same way. Like things, for example, those kind of functions. You see, those kind of functions at every point, they sort of smoothly go to 0. Okay, so that's uniform convergence, which is very strong. So if functions converge uniformly, it's good. Basically, their integrals converge uniformly. If the functions are continuous, the limit is continuous. Under some assumptions, the derivatives also converge uniformly. So it's a very nice thing, very nice mathematical convergence. And now let's go to the other side of spectrum. Spectrum. This is not linear algebra, but still. Then there are things that are slightly weaker than pointwise convergence, which is, if you want, called integral convergence. I guess let's call this, L1. Sine of nx goes to 0 in L1, or integral convergence, if you just take the difference of those two functions and you integrate. So sine of nx minus 0 dx. And I forgot to say, let's fix an interval, let's say 0 to pi. If, suppose you take the difference of those two functions, at least in the integral sense, this thing goes to 0. In other words, if you take the integral from 0 to 2 pi of absolute value of sine of nx dx, this goes to 0. In other words, just suppose that somehow the areas, or the absolute areas under those functions go to 0. So we want those things to go to 0. And unfortunately, I believe this is not quite true in this example. So it also doesn't go to 0 in L1, and you can also play with this. There's nothing special about L1, but if you take the square integral, still not true, but if it were true, then this would also go to 0. And this is, I guess, nice in physics, for example, because you can interpret that as the energy. You can sort of say the energy of this function goes to 0, which, again, it's not as nice as pointwise convergence, but it's still nice, and mathematically it's still important. Because, to be honest, rarely in math do you deal with pointwise convergence. When you have a function, rarely do you ask yourself what's the value of f at x. More, usually what you ask yourself is rather, how does f behave with integrals? What happens if I integrate f? Does that go to 0 or not? And in fact, this leads me to the last point, which has to deal with our original question. There's something called weak convergence, which is very weak, but very useful. So, weak convergence. Because as I said, in math we don't really deal with functions pointwise. We actually just, integrate the function or maybe multiply it by a function and integrate it. And this is the convergence that's very well suited to this. And in fact, let me talk about this. In this case, sine of nx weakly converges to 0 on, I guess, interval 0 to 2 pi. So this is sort of like a half-assed, arrow. It's called right harpoon up in latex. And what does that mean? And by the way, there are different ways of defining weak convergence. In this case, if you know more math, it's weak convergence with duality with C1. What does that mean? As I said, usually what we do with functions is that we multiply them. So let's suppose we multiply them by a function phi of x, and we integrate it. So this is very typical in PDEs. For example, you multiply by a test function and you integrate it. If this thing goes to 0 for all phi in, I guess in this case, continuous, once differentiable functions whose derivative is continuous, then we say that this function weakly converges to 0. And this is a very useful, again, way of defining, a convergence of functions, because again, that's the main mode of convergence you're dealing with. And it sort of also makes sense in that picture, because we have those functions sine of nx, which wiggle faster and faster, and somehow this says that if you take the weighted average of sine of nx with respect to any function, then those functions in average go to 0. And this sort of makes sense. You see them wiggling, 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 but they wiggle around from top to bottom, and on average they go to 0. And by the way, depending on your space, you can have different kinds of weak convergence. There's something called convergence in distribution, where you just take smooth functions, infinitely differentiable functions with compact support on 0 to pi. You could also have weak convergence in L2, which is also useful, where you just take phi to be in L2 from 0 to 2 pi. So many functions are in there, therefore it's slightly harder to converge weakly to 0 in this case. And by the way, you can also replace this with f. If this goes to f of x, it means that the average of those functions converge to the average of f of x. Yes. So somehow, f of x, phi of x. Phi of x dx. So we say this function goes to phi if you multiply. This function goes to f if whenever you multiply it by phi, the average goes to f times phi. Also very useful. And now enough talking, let's do some math. Let's actually show that this thing goes to 0 as n goes to infinity. So let phi be, again, once differentiable, and moreover the derivative is continuous, then let's calculate integral from 0 to 2 pi of sine of nx phi of x dx. Okay, ideally we want to show this goes to 0 as n goes to infinity, and here's a useful thing. We notice phi is once differentiable, so we sort of want to put a derivative on this phi, and the way to do this is simply by, ta-da, integrating by parts. So if you integrate by parts, this becomes, I think, minus cosine of nx over n. So you anti-differentiate this, so AD, and then you differentiate. So phi of x, again, from 0 to 2 pi. And then minus integral from 0 to 2 pi, maybe here, of minus cosine of nx over n phi of x dx. And now let's just deal with that. So that's just minus cosine of, man, I should have used pi m, but okay, 2 pi n phi of 2 pi plus cosine of 0, I guess, phi of 0, and all this divided by n, and then plus integral from 0, I forgot the important thing, phi prime, from 0 to 2 pi cosine of nx phi prime of x over n dx. Alright, and the nice thing is this you can evaluate. Cosine of 2 pi n is minus 1. Sorry, cosine of 2 pi n is 1, so we have minus 1 here. So minus phi of 2 pi plus phi of 0 over n. Okay. And then plus, I guess, 1 over n, integral from 0 to 2 pi cosine of nx phi prime x dx. Okay, and now remember what our goal is. We want to show that as n goes to infinity, this whole junk goes to 0. But look, phi doesn't depend on n. So those are just two numbers. Think like 5 over n. So as n goes to infinity, this thing disappears. So as n goes to infinity. And moreover, I'm claiming that this also disappears, and all we have to show that this is bounded. So now let's deal with the second part. So, and moreover, remember to show something goes to 0, it's useful to do it in absolute value. So 1 over n, absolute value of the integral from 0 to 2 pi cosine of nx phi prime of x dx. First of all, you use a triangle inequality. 1 over n, integral from 0 to 2 pi, absolute value of cosine of nx, absolute value of phi prime of x dx. Now remember, even though cosine wiggles like crazy, it's still bounded. In other words, it's still less than or equal to 1. Which is nice, because this precisely gets rid of the oscillations. So we did something good. And now, here is where I use the assumption that phi is in C1. Yeah, C1. What does that mean? Again, first of all, we can take a derivative of phi. That's why this worked. And moreover, the derivative itself is continuous. So if you have the interval 0 to pi, you can think of phi prime as being a nice continuous function. And remember, here's the important thing about continuous functions. If you have a continuous function on a compact interval, then it is bounded. In other words, it's squeezed between a number m and a number little m. Okay? Or it could be negative, but the point is, in absolute value, this function then is less than or equal to some constant, which doesn't depend on n. And so in particular, this whole integral is less than or equal to 1 over n, this constant which comes out, integral from 0 to 2 pi 1 dx, and that's just 2 pi c over n. Pi c's. Not my zodiac sign, but anyway. And now, remember, we still want to show it goes to 0 as n goes to infinity, but notice the top is a constant, the bottom is just n. So indeed, as n goes to infinity, this goes to 0. So in the end, after after this integration by parts, we've shown that sine of nx, phi of x, from 0 to 2 pi dx, it goes to 0 as n goes to infinity. So in particular, these two functions, sine of nx, they actually weakly converge to 0. Alright, and by the way, here I use the assumption that phi is in C1. Turns out with an approximation argument, you can also show that it goes to 0 in L2. So it weakly converges to 0 in L2, which just means you replace phi by L2 functions. And not only that, same thing holds true for cosine. So also cosine nx goes to 0 weakly. And not only that, if you combine this, you get ei nx goes to 0 weakly. And by the way, which also corrects a slightly non-rigorous argument I made in the integral of sine of n squared, or sine of x squared, because I said somehow the boundary terms go to 0. Well, it turns out even though this oscillates like crazy on the circle, in a weak sense it actually goes to 0. Alright, so I hope you enjoyed this little analysis excursion or extravaganza. If you want to see more math videos or more analysis videos, please make sure to subscribe to my channel. Thank you very much.